All right, today we are going to look at chi-square analysis, what it's used for, and how we can apply it to a couple of problems. Chi-square analysis helps us in a mathematical way determine the relationship between the variables in an experiment. It allows us to see if the results that we get, the things that we observe, match up to what we expect. It's called a goodness of fit test, and it makes it so that we don't have to arbitrarily decide if our data more closely represents what we expected versus if it mathematically represents that we expected. So for each of these problems, we're going to write a null hypothesis that is abbreviated H sub O, calculate the chi-square value, and use a critical value table to indicate whether you reject or fail to reject the null hypothesis. This is the critical value table that we'll be using. In biology, we're always going to use this table with respect to the p-value being 0.05. In other words, we're only going to use this part of the table. We will not use the p-value 0.01. Okay. So if you kind of follow along with me and set up your problem the same way, I think it really simplifies it. You'll need a calculator. So a zookeeper hypothesizes that changing the intensity of light in a primate exhibit will reduce the amount of aggression between baboons. In exhibit A with low light, so I'm going to kind of underline that because that's my first category, a low light environment. He observes 36 incidences, that's my first observation, of aggression over a 1 month period. In exhibit B with normal light, so there's my second set of conditions or my second category for this problem, and we have 42 incidences of aggression. Do the data support or refute his hypothesis? Now remember, he hypothesized that light intensity, if you have a low light intensity, it could reduce the amount of aggression in these animals. So first we're going to write a null hypothesis, and the null hypothesis simply states that there is going to be no change, or that there is no difference between what you expect and what you observe. We'll be hearing some bells during this. So in this particular one, if his hypothesis is that the light will affect aggression, the null hypothesis is that light will not affect aggression. Light levels will not affect aggression. In baboons. I think I spelled that right. Too many B's in there. But you get the point. So basically the null hypothesis is kind of the opposite of the hypothesis. And we're saying that it will not affect baboons. This null hypothesis will inform our expected values. So the chi-square formula looks like this. Chi-square equals the sum of O minus E squared divided by E. So we'll kind of look at this as we go. The chi-square value is what we're trying to figure out. All right, so first, the bulk of your solving occurs right in here, O minus E squared over E. So the first thing I'm going to do, O stands for your observed data, so I'm going to go back up to the problem to get my observed data. I've got 36 incidences of aggression with low light, so for low, I've got 36. And then in exhibit B with normal lights, I have 42 incidences. So normal, I have 42. So that's what I put down first because that's simply what's in the problem. And basically if we just look at the data without figuring it out, it does look like normal light causes greater aggression. If we lower the light, we have less aggression. But we don't need to just look at those numbers and say, yeah, that looks like it supports his hypothesis, because maybe it does, maybe it doesn't. That's what the chi-square is for. The next column that I'm going to make is my expected. Well, if I didn't expect light to affect aggression, how many instances of aggression would I expect in low versus normal light? So the first thing that you do after getting your observed is to add them up. I have 78 total instances of aggression. If I expected no difference between light and normal, what would my expected be? Well, I'm just going to take that and divide it by 2. That's what I would expect. If I had 78 instances, 39 of them should have been low light and 39 of them would be in the normal light. That gives me my expected. Next is where you do your math, and you can pretty much just do this in the calculator. O minus E squared, don't forget to square that, divided by E. So I'm going to take my calculator. O minus E, so the difference between O and E we can see is 3. 3 squared is 9. So I'm going to take 9 divided by my expected. 39 was my expected. So on my calculator, 9 divided by 39 equals 0.23. So I'm going to keep 2 decimal places. The reason that I picked that is because if I look down here at my table that I'm going to compare to, there's 2 decimal places there. That's just kind of a good rule of thumb to use. So this is going to be 0.23 for the low light, and now I'll do the normal light. The difference here again is 3. 42 minus 39 is 3. 3 squared is 9. 9 divided by the expected is 39, and again it's the same thing, so it's 0.23. Now the next thing I do, I've done this right here. So that part of the equation is taken care of. This right here means to add up, or the sum. That sigma is a Greek symbol for add. So I'm going to add these 2 values up, and it's 0.46. That is my chi-square value, and that's where you stop. You don't do anything square root or anything there. Your chi-square value is 46. Now, I have to compare that to my critical value table to see if I accept or reject that null hypothesis. Is the low light aggression, do low light levels affect aggression in baboons or not? So down here to the critical values table, you're looking at these numbers here. How do you know which degree of freedom to use? Which category or which column of numbers do I pick? So that's based on something called degrees of freedom. Your degrees of freedom are your number of categories minus 1. So your degrees of freedom equals your number of categories minus 1. I have 2 categories, low light and normal light. So that's 2 minus 1. My degrees of freedom is 1. You're going to go down here to your critical values table. Here's 1. 3.84 is the critical value. 3.84. My chi-square value was 0.46. If your chi-square value is lower than the critical value, then you are going to accept, or in other words, fail to reject the null hypothesis. In other words, you're going to accept that based on the data that you have, you're accepting this, that light levels do not affect aggression in baboons. Even though initially when we looked at our data it kind of looked like it did, statistically it does not. This gives us a statistical way to determine whether or not light affects baboons. And mathematically it does not. If this number, this chi-square number, is lower than your value down there in that table, then you're going to accept the null hypothesis. And I'm accepting the fact that my data show that light levels does not affect baboon aggression. All right, let's look at this next one. So in this one, a scientist predicts that kittens born with a congenital birth defect will be 25% based on the hypothesis that this is caused by a recessive gene in that breed of cat. And after several litters, he finds out that 44 out of 125 kittens had that condition. With genetics, the null hypothesis is based on your assumption about the gene. So if we're saying that basically this gene is recessive, okay? Genetics works a little different than other problems. Our null hypothesis is going to be something along the lines of the observed data regarding this disease is the same as the expected, with a recessive allele. All right, we'll get into genetics later in the year. That's usually where we use chi-square analysis, which is why I threw it in here. So let's go up to our data, and first we're going to figure out our observed and our categories. So based on this problem, we've got a birth defect, or we don't. The cats are normal. And according to the data, 25% should be recessive if this geneticist is correct. 44 out of 125 kittens have the defect. If 44 out of 125 have the defect, how many should be normal? Well, 125 minus 44 is 81. So if I have 44 with the defect, 125 total, then 81 should be normal. Now what do I expect? Here's what I expect. 25% to have the disease. So go to your total. If I have 125 kittens and 25 of them have the defect, or 25% have the defect, 125 times 0.25, which is 25%, gives me 31.25. So we'll say 31. So I have 44 with the condition. I expected 31. Is that too far away to say that this congenital defect is not recessive, or is the difference is just due to chance? That's what the chi-square will tell us. Now, what would I expect to be normal? So I'm going to take my total again, 125. If 25% is recessive, that means 75%, or 0.75, should be normal. So that's going to be, we'll round that up to, 94. All right, then we're going to do O minus E squared over E. So right here, the difference between 44 and 31 is 13. 13 squared is 169, and then we're going to divide by 31 because we divide by the expected. Divide it by 31. And that gives us 5.45. And then the difference here, 81 from 14, again, that is 13. 13 times 13 is 169, and I'm going to divide that by 94 because that's what I expected, which is 1.80. Now I'm going to add that up. And that gives me 7.25. That's my chi-square value. Now I have two categories, so my degrees of freedom is 1, because it's 2 minus 1. So I'm going to go down here to the 1. Again, it's 3.84 for my critical value. Since this number is larger than my critical value, I'm going to reject the null hypothesis. I'm going to reject that this is simply a situation where that recessive trait, that disease, is caused by a recessive gene. Now, what's that mean? That means that maybe it's caused by more than one gene, or maybe the disease is not purely recessive. Maybe it's not genetic at all. We don't know. All we know is we don't have enough evidence to say that it's that recessive gene, so we're going to reject the null hypothesis. Okay, that's it. Hopefully that helps you to understand a little bit better, and we'll work on this in class if you're at home and trying to figure this out on your own. Be sure and watch those videos. They are helpful.